So today we're going to discuss gyroscopes. Now gyroscopes are these sort of magical objects that seem to somehow defy gravity. What I mean by that is there are many types of gyroscopes, but one type, if you have a piece of rope hanging down attached to the ceiling, say, and then you have a wheel on some axle where one end of the wheel is connected to the rope. What we expect is if we had this system and we just let it go, we would expect the wheel to be pulled down by gravity and it just to fall down. But what we observe is that if we have this wheel spinning, so we give it some velocity omega, some angular velocity, then we find it does not fall down. Indeed, it starts to precess around, let's call this the z-axis. And that seems pretty surprising. It seems like it's defying gravity. But we're scientists. We know that it's not actually magic. There should be some physical explanation. So in this video, we're going to discuss a little bit about where this magic comes from. So today I want to consider a couple cases. What we're looking at here is one of the sort of standard examples you have for gyroscopes. And let's think about the forces that are involved in this standard example. So we know there's tension acting up because of the rope. And then we know there's gravity acting down. So generally what would happen is if we have the wheel not spinning, if it's just sitting there, then if we let it go, then we know that there's going to be some torque acting on the wheel, pulling it down. And in particular, we can use R cross F, and we see that the torque is going to cause this object, is going to cause it to want to swing down, and R cross F is this direction. But again, as I said, what happens is if we have this wheel spinning rather than just being stationary, then that's not what we see at all. We don't see gravity pulling it down. We see it starting to precess around. So to think about this a little more deeply, let's look at a different view. So this is our side view. Then let's look at a top view. So again, now this is the top, so the rope would be coming down. And then here's the axle. And we have some wheel. Now it has, we start it rotating, so it has some angular momentum L that is pointing to the right in this case. And then now torque, which was in this view, was into the board, is now going to be pointing up if we're looking down at the system. So what we see is that the torque is perpendicular to the direction of the angular momentum, and indeed it's exactly perpendicular to it. And if we recall our study of uniform circular motion, what happens when an object is moving with uniform circular motion, what you have is you have some constant force that is perpendicular to the momentum of the particle. And if you recall, this particle now doesn't accelerate, it doesn't speed up or slow down, but instead, this force that's acting perpendicularly causes it to change direction. So this is very similar, again, as we know, often things that are rotational are very analogous actually to things that are linear. In this case, we have a torque that's acting perpendicular to the angular momentum, just like in the other case we had a force that was perpendicular to the linear momentum. And what we find is, just like in that case, this torque, rather than causing this wheel to change its angular momentum, the magnitude of the angular momentum, it instead is going to change the direction of the angular momentum. And what we find is that this torque is going to cause the angular momentum that's pointing this way to circulate around. And that's what's causing this sort of circle motion, or this angular precession is what it's called. So something that confuses a lot of students when they study gyroscopes is the fact that there are a couple angular velocities that you can discuss. So the first one is this little omega that we have here, and that's the omega that you initially start your wheel spinning with. But now, as I just said, this torque, we know the torque due to gravity here, is going to cause this to want to precess around the z-axis now. So now we're going to have a second angular velocity, which is generally written as capital omega. And in this picture, this is sort of, this spinning around is now capital omega. So there's always these two different angular velocities that one has to think about, and you have to remember which is which. Otherwise, things will get messed up. So with a bit of work, in this case, you could compute the angular velocity, capital omega, or the rate of angular precession of this wheel. And what you would find is that capital omega is given by the torque divided by the angular momentum. And what I mean by that, maybe I'll call this angular momentum initial, because this is the angular momentum that is due to this initial angular rotation, little omega. So this is the original angular momentum. Again, this is written, so this again would be maybe Li here. So if we wanted, for completeness, the moment of inertia of a wheel like this, where all of the mass is assumed to be at the edges, is given by mr squared. And then the torque, in this case, is due to gravity. So torque, let's call, oh, I have a couple r's. Let's call this guy d, actually, the distance out here. And then r is the radius of the wheel. Then this is d times mg over mr squared omega. And the masses cancel. So dg over r squared omega. And this is what you find if you have a system like this and you start it spinning with some angular velocity omega. This is the velocity that you'll find of the angular precession. Now, I said this is one of the standard examples of a gyroscope, but you can have different types of gyroscopes. For instance, another standard one you see, rather than being hung by a string, it has some support here, which gives some upward force. And in that case, everything works out pretty much exactly the same way, just instead of a tension, you have sort of a normal force that's holding up this side. Now, what I wanted to do is to consider a slightly different example, where now we don't have the wheel hanging, but instead we have the wheel with the axle through it, and then we are simply holding it in our hands. So that is to say, if I were standing here, I have the wheel, and it's this way, and I'm just holding it up with my hands. So again, we know that there will be gravity pulling this guy down from its center of mass. And in this case, these are the three forces as opposed to the two forces you had in the first case. And again, this is the side view we're looking at. And we want to analyze the difference in this case as opposed to sort of the more standard case. So there are perhaps two primary differences. In this case, if you're holding it up, I suppose you could cause it to rotate about many axes, but in this case we want to consider the case where it rotates about its center of mass here, so it's rotating about the center, where in this case this omega is about the z-axis, which is about the end of the rod. And then of course the other primary difference, now if it's rotating about the center, is the torques that you're considering are no longer torques due to gravity, but now are torques due to the force of the hands holding up the wheel. So we'll need, because we have a couple different forces in this case, we will need one more equation, but that's easy. We know that the sum of the forces in the vertical direction are going to be 0 because we don't want our wheel to be accelerating up and down. And that gives us the equation Fr plus Fl is equal to, or it's equal to 0 if you subtract the force of gravity. So another major difference in considering this type of system is here there's some natural frequency omega, capital Omega, which is a response of it spinning with little omega, and it's because of a torque due to gravity. And so you know exactly what capital Omega is going to be. But in this case, we don't know what the forces on the hands are. You could hold it however you want. And so what you'll have is you have some capital Omega, which is sort of forced. So you can cause it to rotate with capital Omega, whatever value that you want, and it's simply going to depend on how much you pull up on or push down on this wheel. So let's say that we want this to process with some given capital Omega, which let's say 5.0 revolutions per second, but it can be whatever you want. And now what we want to think about is what magnitude the forces you need to pull up on this thing with your hands are in order to cause it to process with angular velocity of 5.0 revolutions per second. So the equation we have over here actually still works up to a certain point, indeed up to this point here. You're still spinning it with some velocity omega, you're still acting on it with some torque, and the moment of inertia, or the moment of inertia of a ring, is still mr squared. But in this case, the torque is not due to gravity, but is due to the forces of your two hands. So let's assume this thing is symmetric, so these two distances are the same. So again, we'll call them, if we call the radius of the wheel r, then maybe we'll call these distances. So the magnitude of this is going to be d. And so torque, again, is r cross, in this case, r cross F. So here the torque is coming out of the board, whereas on the other side, r cross F, the torque here is into the board. And so what that tells us is that the total torque is going to be a difference of these two. So it'll be d times Fr minus d times Fl over mr squared omega. So now all we have left is a bit of algebra if we want to determine the amount of force you need to use on your right and left hands in order to get this wheel to precess with an angular velocity 5 revolutions per second. And I'm not going to do all the algebra for you, but I'll tell you the answer. And that's that the force of your left hand is capital omega I little omega minus RMG over 2R. And the force on your right is going to be the same expression, but now with a plus. So you find that the force that you have to have in order to cause rotation of 5 revolutions per second, which you could plug in for capital omega here if you want some exact value, is going to be, you're going to need to hold it with a different force of your right and your left hand. Of course, again, going back to the case where the wheel is not spinning, if it were just stationary, then you know the weight would need to be split equally between your right and your left hand. But in the case where you have angular precession that you're causing, you're going to need to have a different force on your right and your left hand. So again, these things are seemingly magical, but are not. Really, we know all of the equations that we need to mathematically describe them and predict their behavior. And if you're solving problems, when you're thinking about, when you're solving any problem of gyroscopic motion, the thing you need to think about is that generally what you have is some wheel that's spinning and then some torque, and that torque in this case could be due to gravity, or it could be due to your hands, or it could be due to whatever it is that you want, whatever you want to apply the torque. And then that torque, if it's perpendicular to the direction of the angular momentum, it's going to cause the direction of the angular momentum to rotate, and therefore it's going to cause the wheel to precess. And all of the problems can be treated in this same way using sort of this basic formula. And it doesn't matter what the torque is, or you could have, for instance, I was considering the case where the wheel had all of the mass at its edges, but you could consider a disk that's spinning, in which case I would be different, but everything else would be the same. So I hope that helped clear some things up. Thanks for watching.